It's time. What I got for today is measurements in the complex current network. What happens with the measuring instruments in case we are not in ideal condition of nice sine or nice DC? What if we try to measure real current, real voltage with a complex nature? First, I would like to pay tribute to the old technique, to the old school. What kind of measurement instruments we had before? Moving coil, moving iron. In Latvian, they were electromagnetic for moving coil and magnetodynamic for the electromagnetic for moving iron and magnet-electric for moving coil. Okay, let's start with moving coil. I have this. Let's show close for record. System, what we got here. Magnet system and frame of wire in the magnetic field. Make it more visible. This one is very nice example. It's so-called Arsenval system. Here it is. Make it visible. It's an Arsenval system. Idea: we have magnet placed horizontal, large, and a wire frame, moving frame in the magnetic field. As a suspension here, flat. One second. Thin, flat spring. All the weight of the frame is suspended on this flat frame, so it gives a resistance moment, returning this frame to its initial position. And here, it's so-called Weston system. Return is inserted with the kind of helix springs. Here we have flat spring. This system is more sensitive. And deflection angle is controlled, or let's say indexed, on the this Weston system. With the index, here light beam was used, or laser if you have it. It will be deflected by the small round mirror. So idea: we have a frame with the current, coil, say coil width, length, it would be 8 bit, inside magnetic field width be induction. Working from the top. Spring returning. Index showing angle of. So, if current flows, what we will see? We will see moment trying to rotate it because it's a Ampere law, Ampere idea, wire in the magnetic field. We will have moment trying to turn it, let's say, this direction. If current flows like 1 second, current flows down, induction, yeah, this way. Coil is coil tries to turn this way, and spring returns its back with the moment M spring. If our instrument is showing something, in its table, current moment is equal with the spring returning moment. Usual in the measurement techniques, linear springs were used. So, spring moment is simple R multiplied by constant Vs, which is dependent on spring design, material and material. Current moment in case of DC will be induction, length, width, number of turn, it will be, and because I use double, and current. Or simple metrology constant, okay, like this. If moments are equals, we will have alpha being A n is divided by spring constant current, or meteorological constant multiplied by current. Here ends typical metrology book. But this text is for DC regime, for direct current. And what about AC? Here I have nice, this one is moving coil, and I have a nice sign, AC. This one, for example, it's clearly moving coil. You can see coil moving, but it's volts AC. How? Easy. Just take one diode, switch it in series with the moving coil instrument, add one more for symmetry, and you get AC voltmeter. Something showing AC. Or, of course, if you like, you can buy more diodes. This will be AC. indicate this. It's something showing AC regime. But what it's showing in truth? Rectified voltage. First, yes, it shows something connected with the rectified current. First, I would like to show small. I have this nice demo instruments. I don't know why it's pretending to be an ammeter, not important. Let me switch. Come close. Yeah. This demo instrument from the school physics. This way. Our boy. Low frequency voltage. Oh, here it is. Scope. One second, I'll scope close. Here it is. Low frequency voltage applied. And what we see? Lower frequency. At this moment, we have current moment. We saw what? Current moment and alpha, the linear function just multiplied of the DC current. If now current is a function of time, changes, moment also will become a function of time. And we see I have a sign of the low frequency, and my instrument follows this sign. It's okay. But what will happen when I raise the frequency? Oh, I'm raising the frequency. Amplitude lower, and final it stands still. Somewhere at 30 Hz it stands still. What happens? Problem with mechanical system, it's a mechanical system, it's inertia. And on a low frequency it follows. But on a higher frequency, inertia prevents its mechanical system no longer follows. And what we can say, what moment is in our case integral some constant becomes an integral of the current. Because mechanical inertia prevents system from moving with the current when the frequency is above some critical moment dependable on design and mostly weight mass distribution of this movable system. It can be used. Wait, please. I have this nice example. It's called ballistic galvanoid. Ballistic galvanoid, this one is very strong structure. What's the idea? The same idea of ballistic to have frame with the current and mirror on a flat suspension. Current flows here in the frame, but also frame has weights attached. Suspension is designed with less resistance moments as possible, but this weight ensures high inertia. The system has inertia of 45 seconds. So angle at which frame rotates will be integral 0 current. Legends tell what they all are producing during the Second World War, and Legends say that these were designed to catch German submarines. Coils were placed in narrows near British coastline, and if steel submarine, which has its natural magnetic field, passes this coil, induced voltage was integrated by these devices, and the key idea, time constant, this integration constant, was selected to prevent fail strips by small bolts or something like this. Only submarine large enough integrating its magnetic current will trigger the system. Nice example. So, returning to ordinary tools, we'll see L being meteorological constant multiplied by average of the current or voltage absolute value or in case of full rectifier, this one in case we have 4 diodes, or drive when is greater than 0 in case we have only half. Current is flowing, but this measurement shows nothing. In our case, I can rectify it and show something. Let's take this one. It's a good quality. It was a good quality instrument. Yeah, I have 20. Q and Y. Okay, what I got here? Quite good in its time. Instrument, it's a rectifier system. I have applied nice sine with the effective value of 20 volts, and it shows nicely 20 volts. My test circuit isn't very simple. It's 24 volts DC. This point is person. Yeah. And then condenser to pass an AC component. Here I have maybe this is ground. How to draw it better? Okay, this one is my test signal, and here I have a signal generator on a primary coil. By shifting this one, I can apply DC offset, DC component. And this one is programmable. I can operate with first, say 1 omega, and so on. I can select Fourier law components from my large generator. Now I have nice sine. Let's apply very familiar third harmonic. I'll set effective value back to 20 volts. Effective value of the signal is 20 volts. We have 20 there. Wow. I'm changing only angle between third and first harmonic. In this position, reading is 17 volts. In this position, reading is 20. So 3 volts difference only from angle of the in this position with less effective in 20 shows 19.2. The lower position 70. And what about DC component? Let's check. I'll correct. Maybe 1 second. 20 AC. At this moment, reading should be 23. It's 22. Reading should be 24. It's 23. Case the worst scenario 17. This one should be 20, it's 20. Should be 24, it's 22. Should be 23.5, it's 22.5. So we see error. Not fantastic, but we see difference. 3 volts from 20. Additional error, some 15%. Not a disaster, but this one, precision class. I think it's 1% or maybe even 0.5%. So we will go out of precision class definitely. We try this one. One second, I'll take attachments. 60 volt scale. 20 shows 20. This way, see, 10, 15, 16, 17, shows 7. Applying DC component should be 25, 22, again should be 24, shows 20. Not ideal, it's what it is. What's the alternative? Moving iron. Here I have disassembled moving iron and metal. We have flat coil here and a kind of small bundle. This flat steel. See. The steel flat vein goes inside the coil. Good thing with moving iron instruments, what in theory they are showing effective value, but they are highly limited in frequency because we have inductance and losses, but that's not always. For example, I have this moving iron voltmeter. Look what will happen when I attach it to the metal. Can you see? It's loading network so hard, puts so large burden on the network. In a 30 volts, it has only 1200 ohm input resistance. Moving iron instruments are known for high consumption from the network. They are showing effective value, but put a high load burden on the network. You can see clip on generator. Load is so high that the network can supply the current necessary. In theory, at this moment I have 17 volts approximately, and it will definitely end at 8. It will be 16. I have 16.8 here, and here it will show 16.4, something like this. They are showing effective value, but it will stop correctly. But put a high load on the network. Okay, what else can we? Dynamometer system. Usually they are wattmeters. We have stationary coil. Appear here. What we got here? Yeah. We have a stationary coil here, two symmetrical coils in black, and inner moving for voltage. Here it is inside. Movable coil. Usually Such kind of instruments are used to measure power, and they are precise until coil inductance start playing its role. They introduce additional inductance into network. So usually they are designed for 50 Hz or 400. Rare models are for up to 10 kHz. They are limited in frequency. Mostly are power meters, watt meters, but also here it is, voltmeter or the dynamometer system. We have a nice indication for network of 100 volts. It will introduce resistance of 1700 ohms. Quite a voltage. What good in such instruments? They are showing effective level, and they are well protected from outer magnetic fields. Horizontal. Time. Oh. Of course, we can say what that's all is archaic and obsolete. Why not? We're speaking about digital instruments. Okay, let's start from this one. It's from high end. To show us effective level or errorness, we need to get square root 1 against from the time, or let's say voltage, time square, we are measuring voltage. Meaning, what we need to calculate, square root 1 against sum, when I change from 1 voltage measurements number I squared. So if we have, I don't know, some periodic voltage, samples should be taken. This one, let's say, is first number I, and this one, the last one, number n. And squares of the sample should be summed, and square root should be taken. Let's see. Volts, do not protest. You measure voltage. 3. Yes. One moment. Effective value of the signal is 20 volts, and it shows us 20 volts. Yeah, 20. Let's take this experiment with the third harmonic. 20, still 20. Good instrument. Until I apply DC offset. Real effective of this signal, it has a DC component, is 23 volts. But our instrument still shows 20 in opposite direction. 24 should be 24 because it has a DC component. This one shows only 20. It's a common problem for modern digital instruments. They do not compute DC component of the signal. If I switch to DC mode, yeah, I have 12 volts of DC, it's true, but without AC part. In the AC regime, it shows me 20 volts. It's all this. If I switch off DC offset, 20.2, okay, it's more precise than my scope. It's okay for some of, I have here what, first and third harmonic. For some of first and third harmonic, it's okay. It's really 20 volts. It's precise. 20, 19.99, it's okay. But I have applied DC component. Now effective value of the signal is 24 volts. I have DC part here, but my instrument still shows 20 because it removes DC component. It's quite an ideology. Can take another one. So, digital instrument, precise, but ignores DC component. Which one to torch? Ah! Let's take this one. Yeah. Okay. 20 volts appears to be precise. I have added DC component. Now, effective value of the signal is 24 volts. I have shifted it. But here we still see 20. Same thing. Measuring system, let's say, removes DC component. If I switch to DC mode, 0, 12 volts. So again, It's a common moment with many modern tools. They do not count correctly DC component. Let's see what we got. This one, no. Where? Oh, yeah, I see. Nineteen nine. 19.9. Looks stupid. But this instrument has a magic button, AC plus DC. Scope think it's 24. This one calculates 23.67. I think this one is more is better. Pure AC 20 19 94 with DC offset 2366 24. So this one the only in my collection measures precise. If you activate correct measurement function in the AC mode, it again ignores DC component. To make box, this one cheap voltmeter from common is here and voltage is here. This is off. Is it visible? Yeah. $20 volts, 19.1. Okay. Should be still 20. Everything it's 16. Now let's apply $20, $19. Should be 24, 35. In opposite direction should be 23. In it shows 7.2. I think it's a disaster. Should be 24. We see 5. should be 23.1, 7.2. I think it's not a voltmeter. I think it's a disaster. Why? Because they use an amplitude detector. Right, one more bit here.
So they just get amplitude and
They have one diode capacitor. Yeah. Get amplitude of the positive wave and put it to the analog to digital. The old monster. A very old model of the digital instrument. How to connect it? Remains. If not here, yeah. Volts. Something happened. No. Ground should be here. Voltage should be here. First should be 20. Show 16. Should be 20. Shows 19. 1 second. Let's check. 0 is 0. And it should read 8, 9, and 0. 8, 9, and 0. Should be 20, shows 18.9. Should be 20, but reads 16.8. And if we apply DC offset, should be 24, but reads 16. Should be 24, reads again 70. It measures the amplitude voltage of AC component. In reality, they only put some mass inside, knowing what effective of the AC, pure AC, is 1.4 higher than 1.4 lower than the amplitude. Take amplitude, divide it by 1.4, and you get effective for pure sine. I think that's what it's done here. Should be 24.7, reads 16. Should be 20, 16.8. In this mode, 16.8. And it's stable. Again, if I switch to the, let's say, quite pure sine, remove the third harmonic at all, should be 20.3, calibration, 8980, I should say. Zero, 19.82 instead of 20. We got what we got. If I add some third harmonic, should be 24.4, we have 17.8. And you can see 22, 23. Should be 22.9, okay. 1. Should be 20, we have 20.2. Should still remain 20, we have 16. Should be 20, and it's 20. I'm just changing the angle. Should remain 20, but we have 15.6. Not an ideal instrument. I think it should stay in museum. But Nixies are nice. What can we conclude? Moving coil instruments will have error in some 10%. Moving iron, okay, but limited in frequency, and put a high load on the measured circuit. Dynamometers, okay, but we need to count the inductors they introduce in the network. Cheap digital instruments from maybe somewhere near to absolute nonsense. Expensive instruments may show correct but ignore DC component. So if you don't know what's going on, take a scope. Also, it's a capital question. What happens with the energy measurements? Count. Yeah, count. They are two kinds. Old mechanical with the disk and newer digital. Which one to open? Maybe this one. No. I don't. It's mechanical, it's nice for payment, but you don't see a coil. Yeah. Is the old method. What we got here? Voltage coil, current coil, and the rotating disc connected to the counting mechanics. Such kind of method counts rotating moment is a multiplication of current. We have one voltage flux vertical and two current flux around it. So it counts a multiply product, and in theory it's precise. In theory. In reality, what will happen? The voltage coil has a large inductance. It has a large resistance for 50 Hz and much higher resistance for higher harmonics. That means what? Current flux will contain higher harmonics, but voltage we see a sharp. In voltage flux we will see sharp decay on the frequency. That's why such methods account correctly only, let's say, third and in some degree fifth harmonic. They do not account higher harmonics because of large inductance of the voltage coil. It's a time-consuming experiment to check it in theory. It was used to steer this moment of voltage coil inductance was used to steal electricity, artificially disturbing load with power electronics to consume some energy at higher frequency. But such methods mostly in our country they all are scrapped. Okay, maybe better to say all retired. Some may remain as a private. Some landlords may keep them, but as official for official billing, they are all phased out. You can use such method for official billing anymore. Today we have digital methods. Where am I? Like for example this one. Sometimes they suffer a little damage from the current. What's interesting, it's a three-phase meter and we have a separate channel for each phase, but voltage connection, if we check for connection, I see something like capacitor and resistance. They don't have a voltage transformer. Current measurement is taken from the shunt resistance, and I don't see a correct precise transformer or something like this for voltage. I'm afraid this capacitor is in the voltage network, not only power supply. This means what DC component will be ignored. Where should DC component appear in ordinary network, power network? And other higher harmonics, I think, will be accounted correctly because it performs a Fourier transform, I believe. So this pure. A bit burnt. Possibly accounts correctly. More expensive commercial methods produce alarm signal if see huge disturbance in current. They assume that it's a fraud attempt. They have such a safety mechanism. If current is unusual, far from sign, high range meters produce a warning signal. Something is wrong, possible fraud attempt. The same way they do if voltage is disturbed. If they see current without voltage, it's a reason to produce alarm. Someone is tampering with the meter. Okay. I have sequenced or sequestered all formulas. I'm not sure they are needed. Oh, I forgot one system. Capacitance. I took my kilovolt meter and didn't return. For measuring of high voltage, capacitance system. One moment. Possible it's still available. I'm not sure. Maybe this selling. This bit is still available. 1 second. Yeah, this one moment I will share my screen. Yeah, here it is. This is electrostatic voltmeter. You know its beauty. Available on.
You can say it.
Okay. Kelvin's design. steel vanes and movable one in the middle. It has a very high input resistance, electrostatic, also set of weights. For 20,000 volts. Oh, nice instrument. Good with them. They are producing effective voltage. But such system, small IC was for 300 volts. Usually they are for very high voltages. It exists, electrostatic system. This one was put on sale for 700 pounds and something went wrong. No beats. Very nice example. Results correct. Correct effective value. Electrostatic system works well if you have voltage high enough. One more, what I forgot. For measurements of, mostly for measurements of currents, thermocouple system can be applied. Idea to put a resistor into the complex current network and use a thermocouple, two metals. This thermal voltage will be function of temperature, meaning function of current effective of heat effective. So such instruments will show effective value. Usually they were like this one. It's Western amperes at radio frequency. Thermocouple system. Sometimes some were produced like this one, Chavin Arnaud. Very nice, nicely done instrument. It's a combination of Arson valve, micro ampere meter with the thermocouple, like aesthetic. They are designed to show effective value because they measure thermal effect. Yeah. This assembly also can be interesting. It has in its core this lamp or valve. Can you see it? What's inside? One moment, I'll draw. one element is a thermoresistor. Element which changes its resistance as a function of temperature. And another one is a heater. Here they are in the vacuum to get a well thermal insulation. Inside it's a thermocouple, heated thermoresistor. Then, if you remember Wheatstone bridge, here we have a motor, sliding contact of the bridge. So, it's an automated Wheatstone bridge which reflects resistance of the sensor. And it was a scale in relative values. When bridge is balanced, we can read resistance in the, let's say, in percentage corresponding to thermal effect of current flowing through the sensor. It also measures effective value, but very slow, because mechanic balance of the bridge takes time. Also thermal inertia takes its toll. But it was used to measure output of communication equipment. Such system will yields an effective value, only very slow. Thermocouple. Thermocouples were natural for what I see, pure moving coil instrument. Let's see. Coil, there was magnet, and a small helix spring. What else? Sometimes student system was used. Students were ordered to take a shot from the scope and perform an integration by the hand to find the real effective value of the scope. Many pretend to measure effective value, but only few do it real. Okay, I think it's enough for today. Let's see. Okay, I'll take a screwdriver and show one interesting instrument. Very unusual. It's a very unusual design. One second, I'll open the case. Slip along. One moment, I'll open the case. Another version of dynamo. It's an early, let's say, edition. Let me come closer. Do we see? Wait a second. This way, and a bit. Can we see what's inside? No. Not enough one. Maybe this way. And sharpness. Okay, it is. Yeah. It's a dynamometric system, but differences. What coils are flat. These are current coils, and inside, swinging, is a voltage coil. Let's say voltage. In fact, they are here. The net is fixing and swinging. This one is intended to show only zero on the system. Round one turns and has an index to show something in numbers. Here, reading is in different way. We need to turn this upper limb. It has a spring connector, and we need to set this index at 0 point here, and later read some related values from the upper scale, and somewhere should be a chart. Which number at the upper limb corresponds to which power? No. Real reading of watts is from chart, converting these related values. It's from 0 to 500 to the real watts. And in the index always should set to 0. Should be set to 0 position, because of a very limited swing angle. The system is flat by its design. Not for traditional, say, for this one. We see only outer coils. This system is like a ring inside cylinder. This system is flat and has a here, in theory, ring can rotate full 360 degrees without any problem. But in this system, rotation is limited to some plus minus 10 degrees. It was believed that such system is more precise. It's an early and later. It's become obsolete because measurements are very hard to perform. Oops. But in theory, it measures. It can be used to measure effective values of current or voltage. Just calibrate it and account load, because resistance of the fixed is 74 ohm and 38 millihenries, and swinging has resistance of 11 ohms and 0, it's 2/3 of the millihenries. So it was calibrated in 50 milliamperes, that corresponds to 500 division. Such beacon tower. Oh, beacon tower, put me. Sure. It has a marble foundation. To make to be stable, this part is from marble. Yeah. Now it's definitely enough for today. No viewings touched. So I can end for today. Maybe some questions.